5.4 is talking about best fitting lines. We spoke of this just a little bit when we were doing some scatter plots. So in this lesson, you will learn how to write a linear model to represent a collection of data points. In real life, there is no single line that passes through all data points. So you try to find the line that best fits the data. And that's what is shown here on the right, and we call it the best fitting line. There is a mathematical definition of the best fitting line that is called least square approximation, and many calculators have a built-in program. So we're going to go through this just a little bit quicker so you get the main idea of it. So in example 1, the data in the table shows the forearm lengths and the foot lengths without shoes of 18 students in an algebra class. So just real life data here. And after graphing these points, you could go ahead and draw your line, your best fitting line, that would most closely fit the data. In drawing that line, as you can see below here on the graph, you can see that if we wanted to hit the most points, we're drawing a line as shown. And why do we do something like that? We can then make an assumption and tell what we think is going to be happening. So if you look here, it seems to be that the longer your forearm is, the longer your foot length will be as well. So if we were going to go ahead and we are going to use that the next thing we could do is find the slope of that to find how much it increases or what rate it changes. And so when we do that, we can look at any of the 2 points. So they used 19 and 20 and 26 and 26. And we're going to go ahead and find the slope of that line. So the slope of that line then would be 26 minus 20 and 26 minus 19. Whoa. And that's going to equal 6/7. And again, when we're dealing with data, we could say that's a change of 0.86. Moving on to example 2, we're going to talk about some discus throwers. Again, we have 2 sets of data, so those are going to change into our coordinate points. One thing to look at is, again, think about how you would set up your graph. We're going to be comparing what happens between the years and then also how that affects the distance. That's the rate we want to check. So the years are going to change into our x coordinate points and the distance will be our y coordinate points. So if you look here, they went ahead and I'm showing you the solution. You can pause, read through this, and see it's the same routine as it was in example 1. So it says next find 2 points that lie on the line to find the slope of the line. Again, to find out what the rate of change might be in this particular situation. So we're going to go ahead and again, using those 2 points, very simply, m equals 230. If I can rewrite that for you. Try it again here. Looks like our connection is having some problems again. One last try, then we'll give up on it. M equals 230 minus 138 over the difference between the x's, 96. So again, remember to go to the same one, minus 8. I chose to go that way, so I could have a positive. I have 92 over 88. And so that's a rate of change of about 1.05. You'll notice then they plug that back in to the slope-intercept form. And so we're doing the same as we were doing with 5.1 to 5.3, lessons 5.1 to 5.3. So to determine the correlation of x and y, you're going to notice that this looks very similar to when we were showing the different types of slopes of a line. When we have it going this way, that's a positive slope. We call it a positive correlation. When it is going in this direction, that looks like a negative slope, negative correlation. And this one with the chicken pox all over the place, there is not a best fitting line, so then we say relatively no correlation in such a situation. I think there's one more example here. Yes, using correlation. So in swimming events, performance is positively correlated with time. The two graphs show the winning 100-meter women's freestyle swimming times and the winning women's long jump distance for the Olympics from 1948 through 1996. Which is which? And explain your reasoning. So if we look at it, it looks like we don't have a perfect best fitting line, but we can at least see that the trend is that it is increasing. If we look at this other graph, we notice that a best fitting line would show a decrease during the times. So the first graph must represent the long jump distance because the winners have tended to jump farther with each Olympic year. The second graph must represent the swimming times because the winners tended to swim faster with each Olympic year. The first graph shows a positive correlation between the year and the winning distance, and the second graph shows a negative correlation between the year and the winning time. And that concludes lesson 5.4 on best fitting lines.